Hey everyone. So this is just a little addition to the material that we learned yesterday when looking at current and voltage and resistance of wires and electrical systems. So something to tag on to the end of the resistance part is resistivity. So resistivity is Uh, a measure of the resistance of a given size of a specific material to electrical conduction. So what this is saying, here's a table of a few values here, is each material that exists. We make wires out of a lot of different things. We can make wires out of copper, silver, gold, or various other conductive materials. But each material, some materials conduct better than other materials do. Okay, and this property of conduction we call resistivity. So here are some tables in the value below you can take a look at. These values are given at a particular temperature because increasing or decreasing the temperature of something also affects a substance's resistivity value. We saw previously with resistance that resistance is proportional to the length of the wire and the area of a wire. Okay, so the longer the wire is, the more the current has to travel, the higher the resistance is going to be. And with area, we see the area as an inverse proportionality here. So with area, the bigger the area, the easier it is for things to flow through the wire because there's more space to move. Generally with wires, when we're talking about area, if we think of a wire, right, the end of it is a circle. So if we think of the cross section of a wire, if you were to cut a wire in half and look at it head on, you'll have a circle. So generally when calculating resistance for a wire, when we're looking for the area, we're just using the area for a circle, which we know is pi r squared. Okay, so this is the proportionality of resistance. Now by adding in the resistivity factor into this equation, we can change this proportionality to an equation. And we get R for resistance is equal to, that P is the Greek letter rho, which stands for resistivity, times length divided by the area of the wire. Okay, where resistivity is measured in ohm meters. So let's take a look at a quick example of this. So suppose you want to connect your stereo to a set of speakers. If each wire must be 18 meters long, what diameter silver wire must be used so that the resistance of each wire is less than 0.12 ohms? So we don't want the resistance going over this value. So we'll start by writing our information we have here. So our length of the wire is 18 meters. We know our maximum resistance that we can have is 0.12 ohms. And we're dealing with silver, so if you use the previous table, the resistivity value for silver is 1.59 times 10 to the negative 8 ohm meters. And our goal here is to find the diameter of the wire. Okay, so to find the diameter, using the values we're given, we can start by finding the area of the wire. So using our resistance equation, R is equal to rho times length over area. Okay, resistance is 0.12. Is equal to our resistivity value, 1.59 times 10 to the negative 8. The length of the wire is 18 divided by A. So rearranging and solving that for area gives us an area of 2.4 times 10 to the negative 6 meters squared. Okay, since our length is in meters, our area will be in meters as well. So now that we have the area, we know, as we just discussed a minute ago, the cross-section of a typical wire is going to be a circle. So our area is going to be equal to I was about to do the circumference. The area will be equal to pi r squared. Okay, we can rearrange this to solve for r, and plug in our area, so the area divided by pi and then the square root, and we will end up with a radius of 8.7 times 10 to the negative 4 meters, or more conveniently 0.87 millimeters. Okay, we can then take that value of r, because our goal is to look for d, so therefore if we have our diameter is equal to 2r, or 1.74 millimeters, okay, for our final answer.